All right, so today we are going to link the motion maps to position time graphs. So we're kind of making a jump here from what we already knew with our dot diagrams and our velocity vector diagrams to position time graphs. So you guys should have your notebook out. We are going to go into our notebook. We're going to title this 1DK for position motion maps to position time graphs. Motion maps to position time. Okay. Okay. One thing that I wanted to kind of point out before we go any further is that we are in one-dimensional motion. We are talking about one dimension. So that means all of the motion that we talk about today is going to be, and I mean from all of this unit, is in a straight line. So these maps are going to kind of challenge our brain a little to get to really understand that. So the first thing, looking at looking at letter A here, we can kind of see that dot diagrams, dot and velocity vectors can be combined. This is just the only real sentence today. Well, that's not really true. We're going to explain the motion in a second, but complex motion. So we're not just speeding up and slowing down. We are going to go forwards and turn around and stand still. And so those are going to be what we look at today. So let's go ahead and look at A. We are going to put this in our notebook as best as we can. And so when I look at this A, I see, all right, I have velocity vector diagram, and it looks like I have, if I look at my arrow, I have 1, 2, 3, 4 arrows. And those arrows are sort of long. So let's go ahead and put those in our notebook. 1, 2, 3, 4 arrows. And then I have a dot. Then I have another dot. Then I have another dot with a shorter arrow on it. And I have 3 more with those short arrows. So need one more. All right, so and one thing also that we didn't have when we looked at dot diagrams the other day was we have this line on the bottom. Okay, so we're gonna put some labels on this to help us to see. This line right here is our position. This line right here is our position. In a reference to this spot, whatever that spot might be, that is our reference. All right, so some questions that you might be asked. How many seconds did this occur? All right, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 seconds. So this occurred over the course of 9 seconds. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 seconds are shown. You don't have to write the are shown part if you don't want to, but 9 seconds are shown here. Okay. Where is the fastest? Is the fastest when they were going to the right or when they were going to the left? Well, let's see. We have 1, 2, 3, 4 arrows. We have 1, 2, 3, 4 arrows. These arrows going to the right are bigger and farther apart. So this is the fastest section, and this is the slower section. Right? What is happening right here where we have dots and no arrows? Yes. What is happening here? It's the wall. I don't think it's the wall. This is where the object is standing still.
Yeah, bro, that's like the wall. That's like the thing that stops it.
Well, that doesn't necessarily say that the object ran into a wall. It just says that the object is standing still.
Okay? So I said a wall. Look,
All right.
that is a wall.
Let's trace the motion of this object, okay? So if we are standing on the ground, we have 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, 7 seconds, 8 seconds, 9 seconds, and then the 9th second is here, still continuing to move. So, and I started wrong. I started with 1. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So my pin did not go up and down, did it? If my pin is the object, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Were there any hills in that motion? No. All the motion is going to stay on a straight line. Right? That's really important to be able to understand that part. I'm recording that. So the next one, you're going to look at some other things in this example here. What do you think is happening in this example? We have an A and a B. B has an arrow. Let's look at our arrows here. We have 1, 2, 3, 4, 5 arrows for both of them. So they had the same amount of time. It looks like it's about constant motion. It's interesting how when you realize that I'm recording, y'all got louder. All right, so that's essentially what we had from the lesson picture. We have 0, 1, 2, 3, 4, and 0, 1, 2, 3, 4. We have 4 seconds represented. Okay, it's important to realize that when we have a label like this, we have 2 objects. Right? Which of these objects is faster, A or B? Why is B faster? Okay, the arrows are longer. That's true. What about the dots, which is sort of subject to the arrows? They're farther apart. Good. Okay, so A is slower, B is faster. Now, also notice, did A start in the same position as B? No, it didn't. And well, but if we look at B, we had the starting line like we had in the other one in the picture in the lesson. If this is our origin, A started a little farther away. They got a head start and they lost. Okay, so if this were a race, that'd be exactly what we would say. Okay, and maybe this is something nice, like an older brother and a younger brother. The older brother gave him a head start, but still beat him. I don't know. But A started in a different place. Started at different location, different spot. Okay. All right. So 2 objects. This one's faster because the arrows are longer and the dots are farther apart. A started at a different place. So, and you guys did a pretty good job of coming up with that on your own. If I ask you what happened in this scenario, you would say there were two objects. Object B was faster and covered more distance. Object A started at further away from the origin. Okay, so those are the kinds of things you might say. All right, give me a thumbs up if that makes sense. Are you getting that? Kinda. Okay, hopefully we're making sense with that part. And then C is a little different. Let's try to put C in our notebook so that we can look at it. Notice on this one we have that the kind of the location, the position line, and it's marked with meters here. That's going to help us to kind of see. We had 4.
Let's say those tops were like a minute of 1 meter for sure.
My spacing isn't exactly perfect, but that's okay. All right, so we started at 0, went to 2, 4. Okay, so that's essentially what we have. What happened in this scenario? Where did the object start? 0. Okay, what direction did the object go? To the left. Okay, notice these negative numbers. So if we are on a quadrant, we're on some kind of coordinate plane, then we're going to the left. We're going to the more negative in our coordinate plane. So we went left, and then what happened? Let's follow this motion. We went to the left for 4 seconds, or for 1, 2 whole seconds for 4 meters. Then what did we do? Turned around and went right. Kept going right. Then what did we do? Turned around and went left. Then what did we do? Went right. So if we follow the seconds, if we start at 0 seconds, 0, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, 7 seconds, 8 seconds. Okay, so if I count the dots, there's 8 seconds represented here. 8 seconds of time. All right. So if we were looking at this, the object changed direction. Where was its fastest motion? What time frame was the fastest motion? Remember, the fastest motion is the longest arrows. So this is the fastest part. Did they maintain that speed, this object? Did this object maintain that speed? No, because this arrow is much longer than that arrow. Is this arrow longer or shorter than when they began? Is this arrow shorter or longer than this arrow? This one is shorter. So they slowed down. Okay. Now give me a thumbs up if that makes sense. Does it make sense? Okay. All right. So every dot is time. So 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. Now, moving the pen to follow the arrow is a little deceiving. So we want to clarify that misconception. If If I am on my motion, if I am actually moving the object, I would say 0 seconds, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, 7 seconds. I don't know where I lost the dot there, but all of it stays in one line. We're not moving up and down. We're all in one line, one dimensional motion. You tired of writing for right now? Maybe? Okay, let's look at something that might help us. So we're going to look at this moving man PhET simulation and kind of try to understand that. I'm going to stop recording because there's another video for that.